All right, what do we have here? We have a distillation column. We're going to be solving for some, molar flow rates using an operating line in the rectifying and in the stripping section. Then using those operating lines, we can kind of find our um, vapor liquid compositions here in the second part. And then we'll be finding our Q line, which kind of relates to the McCabe-Thiele diagram where we have our operating lines, and the Q line connects the 45-degree line on a binary XY diagram to the intersection of our two operating lines. So we'll just kind of jump in here. Just like usual, I'll go ahead and start drawing. Um, Hopefully this isn't too bad, but we have our distillation column. I'll go with 5 stages for now, and we'll split up these stages. How do I want to try to fit these all in the frame? But we'll split them up into 5 stages, numbering from the top, or I guess 4 stages if we count the top as 0. Again, your position doesn't really matter here, but as long as we're consistent with our numbering, we should be okay. Then we have our incoming feed. Our feed usually is denoted by our feed flow rate F. And then we have our Z component of, in our case, we'll be talking about the more volatile component, specifically referencing our benzene toluene binary composition from previous video. We'll be using that graph and kind of plotting our operating lines on that. Usually with this initial feed, we also have another variable called Q. Q is our liquid fraction of the feed, so it can be either component 1 or component 2, but just putting that out there so when we see it in the code, it doesn't come out of nowhere. Just kind of group these all together. And going up, we have our rectifying section. So I guess, how do I want to label this? Something like that, maybe. Rectifying section. And kind of getting ahead of myself like I like to do. As you go up in this column, you'll have more of your more volatile component. Kind of an aside here. Kind of draw out, if you remember our binary XY diagram, we plotted our liquid mole fractions versus our vapor mole fractions. And if you remember, our curve was something like this, and whether it was constant pressure or constant temperature, we know that our composition favored the vapor phase. And you'll see as we talk about these operating lines, the composition in terms of the vapor molar fraction in relation to the liquid molar fraction, YI will have an increasing component of our YI as we go up the distillation column for our more volatile component. So that's the rectifying stage. Excuse me. Below that, we have our stripping phase or stages, and just kind of labeling out what else we have. So coming out of our top, at the top of our distillation column, we have our condenser, and what comes out of there is our liquid mole fraction of our more volatile component, and we call that our distillate. So that's the mole fraction, and that's the flow rate. Similar on the bottom, we have our liquid mole fraction, and we'll be talking about strictly for our mass balances to help us in that sense as well. Talking about our more volatile component as we do the mass balance. So for this bottom, we have our liquid mole fractions of the bottoms and our bottoms flow rate. And keep in mind, this is the more volatile component. So as we go up, XD, our liquid mole fraction in our distillate, will have a higher purity versus our liquid mole fraction in the bottoms will have very low purity, something like, I don't know, 98 to 2%. That's a pretty good distillation column. So keep that in mind as we go along here. And this is bottoms for our boiler. And the reason why they're called these things, well, we have our vapors going up. I guess it's better to call these separate streams for now. So these are our vapors, or vapor molar fractions, or molar flow rates, excuse me. And then going down, we also have our liquid flow rates. So you can kind of see where this mass balance is starting to all come in here. Going down underneath the feeding flow rate stage, the stripping stage is now we have our same thing, our flow rates going up and down, but now we denote them as V bar and L bar. So still very similar, but just another new notation because, as you can see, L bar, V bar, stripping, the flow rates in the stripping and rectifying stages are actually different as we do our molar fractions, or I'm sorry, our mass balances. And the reason for that is because we have our incoming feed flow coming in the middle, and our molar flow rate V going up has to be greater than V bar because of that additional feed. So if you have something like 1 moles per second of the V bar going up, and then your feed is 1 mole per second, but your Q is 0.5 and your Z is 0.5, then you'll have an additional 0.5 going up in that vapor. So keep in mind these contributions as we're doing our mass balances. Let's just stick with the questions for now. So questions saying we have to assume a constant molar flow rate. So that's actually a very, very big assumption we're making. Another aside here, kind of picture, I don't know, like a liquid composition of some mixture. We'll say, I don't know, it's a 0.5 benzene, 0.5 toluene, and well, actually, let's start with the basics. Forget about compositions. We're going to be talking about pure liquid, pure gas. So we have our vapors going up through the liquid and coming out of the vapor. And I don't think I actually discussed this. So there's liquids coming down and vapors going up. And each of these stages are in equilibrium. And yeah, that's I'll leave it at that for now. But as we get back to our assumption here of constant molar flow rates, let's say we have a vapor going in at around, I don't know, 1 moles per second. So as it goes through that liquid, what we're saying is, well, it stays the same. It's 1 moles per second coming out. But keeping in mind compositions of two different, I guess, in a mixture, if we have something like, I don't know, 0.5 benzene, 0.5 toluene within this liquid, and we say that's in equilibrium, well, in reality, well, actually, here, let me start back here. Sorry about that. And then our vapor is actually, I don't know, 0.4 benzene and 0.6 toluene, and it comes out, I don't know, maybe 0.6 and 0.4. So obviously you can see compositions are not necessarily the same, but our assumption remains the same in that we keep our molar flow rates the same. And normally this isn't the case. Talking about constant molar flow rates, the heat of vaporization, well, the change in that is equal to our normal heat of vaporization and our heat of condensation, or I guess enthalpy, however you want to say it. And this change is what affects these molar flow rates. Say we had, I don't know, I think benzene is around like 30 kilojoules. So I'll just call this maybe 31 and kilojoules per mole. And maybe the liquid mixture is 30 kilojoules per mole. Well, our resulting vapor here might be a little bit higher, since now this change in vaporization, well, we're vaporizing more than what our difference is. They're not equal, meaning we have to have more vapor coming out of this vapor going into a liquid equilibrium stage. So our assumption is that this heat of vaporization is not changing with our mixture. So even though these two stages, I guess two phases, are two different compositions, we are assuming that as the vapor goes through each equilibrium stage and the liquid goes down in our distillation column, that these molar flow rates stay the same. And that is a very, very helpful assumption, as now you can see that all our V's, while they're actually supposed to be numbered, V1, V2, and another aside, as we notate these, I guess, flow rates, we number them in the number, the stage number that they are coming from. So this liquid here is coming from stage 0, so I number it the liquid flow rate of the 0 stage. And kind of going off that notation, I can say something like our V1 is equal to V2. Actually, our V bars are all equal to each other. So we'll be kind of getting rid of these number notations soon enough, but I'll go ahead and number them just for the sake of it. Kind of see that these passing streams are coming from the liquid, the stage coming from above, and the vapor coming from the stage below. That'll be important later on as well. So kind of more of the expressions going on, relating all our vapors together that at least are in the same rectifying stage and the stripping stage, and then the same thing with our liquids. So these are all equal, and that just kind of cleans it up so we don't have to write that notation. So that was the constant molar flow rates, and now that will help us derive our expressions for the operating lines, and we can kind of just start going with, yeah, let's just start with the rectifying stage. So the rectifying stage, well, what do we have? Well, it's our vapor going in, and that must be equal to, well, the two arrows pointing out of this box. So liquid molar fraction, or liquid flow rate coming out, and the distillate flow rate coming out. So let's just start there for our mass balance. All right, just to label everything, rectifying operating line, I like to abbreviate OL. So what did I say? I said the vapor molar flow rate must be equal to the liquid flow rate and the distillate flow rate. What goes in must come out. In equals out. And I can actually get rid of this this notation. And now we'll be balancing with our molar fractions. So we have V. Well, remember that our molar fractions we denote as Y. So this would actually be Y1, and this would be X0. Note that these molar fractions between each stages are not the same. So that is a very important distinction to make. That should be 1. Because these are the fractions going up and down through equilibrium stages. And like I mentioned before, the equilibrium gives more purity to the more volatile component in the vapor phase as you travel up the distillation column. So kind of going off of that, I guess it's good to also kind of visualize what it would be for any number of stages as well. So just to kind of visualize this more clearly, say we have the nth stages, and this is our rectifying stage. So we have our vapor going up, V, or maybe I should just, well, I can label all of these V actually. So I'll just say all of this is V, since remember, they're all the same. We're assuming constant molar overflow or molar flow rate. And then this is our liquids coming down. And remember at the top, we have our distillate and the distillate molar fraction and distillate molar flow rate. And now we have our vapors coming up, which is our vapor molar fraction, Yn, labeling once more our molar fractions. And now our liquid molar fractions, or mole fractions, x2 and xn-1. So remember that we're writing these from the stages they're coming from. So if I write something based on our, how should I say this? Let's just focus on this stage for now. So we have our vapor molar flow rate with our corresponding to a vapor molar fraction of Yn from the stage n. Then we also have our liquid flow rate coming down from the stage above, so n-1, and then with our liquid molar flow rate. So also know I'm writing n so that this can apply to any number of stages, and you'll kind of see this as we plug in numbers. So let's just go with that for now. So we have our Yn times our vapor molar our molar flow rate for the vapor must be equal to the stage coming down from above, xn-1 times our liquid molar flow rate plus our what's coming out at the top, our distillate molar fraction, xd, times our distillate molar flow rate, d. So, I guess it's a good time now to bring up, for rectifying stages, we have something called a reflux ratio, and that's just simply another term we use to kind of simplify things, and it's kind of common terminology when we're referring to distillation columns, and the reflux ratio simply refers to, well, it's a reflux, what we're taking back, and versus what we're taking out, basically. So that would be our liquid coming out from the first stage and our distillate going out. And remember, all our liquids are the same for the rectifying stage, so I can just write this as the liquid over the distillate. And from this operating line equation that we're trying to derive here, I mean, it kind of ends just once we isolate our y. We can actually plot this once we're given some flow rates, and in our coding that'll be kind of more visual, but we can actually graph this as is. But what might be helpful, if you kind of see these equations maybe in the future, you'll know where they come from when they do something with this reflux ratio. So how we're going to relate our operating line to our reflux ratio, and again, this is pretty much optional. We're going to substitute our mass balance up here, so now you know why we did that. We're trying to get in terms of L and D, our liquid flow rate and distillate flow rate, which is why we're substituting our vapor flow rate. And remember, that was our vapor going in here. We were focusing on this top portion. So our vapor going up and our liquid coming down, or our vapor going up must be equal to our liquid going down plus our distillate flow. Hopefully all of that's undone, and we can do that substitution. So yn, our vapor molar fraction, and we're just substituting our vapor molar fraction, our vapor flow rates, with the corresponding expression that we wrote right there, underlined in red. So L plus D. And now what we can do, now we have our terms in terms of L and D, we could substitute R to give our operating line in terms of a reflux ratio. So I'm just going to divide by D, and L over D is R, L over D is R, D over D is 1, and very simple, dividing by D on both terms. The denominator is the same, and yeah, that's our operating line for the rectifying stage. We can go ahead and graph that. I think I'll go ahead and derive all the expressions first, so I'm not switching back and forth. So yeah, let's just go ahead and do the stripping phase now, or stripping region of the distillation column. I'll go ahead and label that stripping operating line. And yeah, we'll focus on this portion here now, the bottoms. Notice this is the boiler, so boiler, reboiler, same thing. We're boiling up the liquid up from the liquid coming down, and that turns into the vapor. It kind of condenses at the top, whole cycle. And again, this mass balance depends on this region here, or at least we're going to be focusing on it, so we can get a relation to our bottoms. So yeah, I mean, this liquid is what's coming down, so what comes in must go out. This liquid flow rate must be equal to our vapor flow rate and our bottoms. So we'll go ahead and write that. Here, I undid all that. Awesome. So our, what did I say? Our liquid flow rate, L bar, remember, because we are underneath the feed composition now. So in our stripping region of the distillation column, we have L bar must be equal to V bar plus our bottoms flow rate. And again, what I did before, I'm going to substitute very similar with the molar fractions. I don't know if this is worth drawing. Yeah, I'll just draw it out. Why not? So we have our bottom here. Like to simplify with the boxes, but works pretty easy. So XB and B. and I'll number them n minus 1 again. So again, vapor going up, V bar, liquid going down, L bar. We have our streams, xn minus 2. Remember to label from the stream that is actually, or the stage that is coming from. And vapor is y, 1, n. So focusing on, again, our mass balance, yn, or you could pick any of these stages, but to kind of simplify when we're plugging things in, we'll do yn and v. And once more, we have our L bar and xm1. So liquid coming down, vapor going up, and then always our bottom flow rate and our bottom mole fraction. So in this case, we actually have our x on the left side, and I'll keep on saying that is xn minus 1, adding our corresponding molar fractions here, writing this out. Awesome. And to graph this operating line, this equation will be, we'll have to isolate it for the y term. So we can actually graph it on the same yx, the binary xy diagram from before. So I'll go ahead and isolate yn. Take this slowly here. We'll subtract our bottoms, or I guess our bottoms term, and we'll have our minus xb b. Do some algebra here, and divide by our vapor flow rate on both terms. So now you're probably thinking, well, we had a reflux ratio for our rectifying stage. What do we have for our shipping phase? And you'd be correct in kind of assuming we have something similar called our boil up ratio, denoted by RB, and it's very similar. It's the ratio between what we're putting back in and what we're taking out. So what we're putting in is our V bar actually, because remember we're below the feed, and that is over our bottoms. So if I want to, again, make our expression in terms of our RB, our boil up ratio, and remember this is optional, I'm going to go ahead and divide by B on both terms after I do my substitution and trying to get these terms in terms of our expression, our stripping operating line expression in terms of V bar here and B. So I'll substitute our liquid flow rates for what we wrote up here. Liquid flow rate equals vapor flow rate plus our bottoms. So I'll go ahead and do that. Yn xn minus 1 and L bar is equal to V bar plus B, dividing by V bar minus xb and B over. Now I'll do something similar. I'll divide by B this time so we can get our boil up ratio here. So V over V bar over B is RB. B over B is 1. V bar over B is RB. And then minus vapor or liquid molar fraction of our bottoms, excuse me. B over B is 1, and V bar over B is RB. So that is, I actually say those are our two expressions for the operating line. So, too bad, just they're just mass. So now that we derive them, we're gonna try to relate them here. So try to use these operating line equations and the equilibrium stages in the distillation column and how we can solve for each composition. So I don't know if it's probably better to draw this out before we code this, so it's probably easier to understand here. I don't know what's easier. I'll go ahead and copy them down so we know what we're looking at. I'll just draw about. I'll go back up since you can see my screen here. So yeah, we have our binary XY diagram here. That's not straight, whatever. So we have our, remember we have our 45 degree angle just to show mainly when the compositions are the same for the molar fractions. And remember, our binary XY diagram has this curve to favor the vapor molar fraction. For our blanking out here, our rectifying stage here, rectifying operating line, we're going to want to graph that. Remember, these operating lines don't necessarily have a physical meaning on every single point. It's just, well, you'll end up seeing that the operating line relates the two streams going past each other between both phases. And that's what we discovered from our mass balances here. So the stage, maybe stage n equals 1, well, we are relating at stage n equals 1. That would be the x0, where it's 1 minus 1, so x0, and then n equals 1, so y1, you're relating x0 and y1. So x0 coming down the liquid, and y1 going, relating those two. Very helpful, actually. So when we do that, when we actually graph these lines, we're going to choose 2 points. So maybe that's what I actually want to start with. Yeah. Yeah, I think I should have copied it down. So yn equals xn minus 1. And I could do it, remember how I said changing or deriving these expressions in terms of the reflux ratio and the boil up ratio respectively were optional. So I'll actually show that to graph these points, you can use either expression. And these points are arbitrary. You could technically solve for any point as long as we're trying to plot the line on our graph. It's whatever you use is fine. So yeah, I'll copy this down and try to get 2 points we can use. So what am I doing? R over R plus 1, R over R plus 1, and plus our distillate, 1 over R. So if you actually see, for one of our points here, we're going to be doing something like xn minus 1 equals xd. So if our liquid molar fraction from the, we'll talk about the first stage or the 0 stage, if that is equal to our distillate, well, you'll end up seeing that our vapor molar fraction must be equal to our distillate as well. So go ahead and do the substitution. xd r over r plus 1 plus xd 1 r plus 1. Well, what do you know? We got the same denominator. We'll end up simplifying down to something like xd, factor that out, and then r plus 1, and r, well, that's just 1. And what do you have? Well, yn equals x. That's a very easy point to plot on our diagram. Well, I don't know, we'll just say some arbitrary point is xd, as xd, and this must be, well, our y. And no, I'll just draw this in terms of, I think I drew this earlier actually, here. So if we assume, well, I use n minus 1, but I'm trying to navigate through all my drawings here. But if we talk about our 0 stage, we can say our x0 here, x0, x0, if that x0 is equal to xd, well, that's our y1. That's just given from the mass balance relating all our expressions together. So I'm going to go ahead and just call that y1, since that's what we wrote on our distillation column. And from this, now that we have a point, we can actually relate this to the equilibrium curve. We have a corresponding liquid mole fraction at that corresponding vapor mole fraction, y1. So again, going back, we have our y1. We actually found this y1 was equal to, oh, what happened? Was equal to, oh, okay. Our y1 was equal to, I don't know why it's doing that, was equal to our xd. And now that we have our y1, well, that corresponds to stage 1, and stage 1 has an equilibrium of y1 and x1. So Remember how I said the passing streams were the operating line, or is how we got the compositions. These compositions are coming from our mass balance, aka the operating line. And now, as we have one stream coming up from the stage below, we can get the liquid molar fraction coming down. So undo all that. So that is x1. Maybe it might be helpful to write these out. So we had our x0. Well, let's just say n equals 1. So we have x0 plugging into our equation must be equal to xd, or we're saying it equal if our liquid flow rate from the top stage is equal to xd, our distillate molar fraction. Well, we ended up saying that our y1 is equal to our xd. So we actually have a point, I'll just call it x0 and 1, and that lies on the operating line. Using that, we have our y1. This is in equilibrium with another point, that is x1. Remember, this is the liquid molar fraction going down from stage 1, and I just like to call this the equilibrium. You can kind of see where this is going. You'll have a passing stream coming down and a vapor molar fraction to accompany that liquid molar fraction as they pass each other. I believe this is y2, but I could check. So we graph that. Well, remember, we come down to our operating line, and that is a new point for our y value, that is y2. And again, if you don't believe me, well, just look at the diagram. Remember, coming down, kind of repeating myself here, but coming down, we had x0 is equal to xd. And because of that condition, we were able to say that y1 was equal to xd. And now that we had a y1, well, now we can get this liquid molar fraction coming down from stage 1. And again, now we have a passing stream here. Now we can relate x1 and y2. So that operating line is very handy when it comes to finding all these compositions, as long as you have a place to start. So again, I don't know if I need to keep drawing this out anymore, but well, x1, y2, if y2. I think we get the point here. If I draw any more, I don't think it'll apply to our diagram, since our rectifying stage stops at stage 2 before we get to our stripping stages. So I'll just stop it there. Oh, I just realized what I messed this up very bad. So actually, what I should have said is that, well, since we plotted it, we'll call this our operating line. Technically, it shouldn't be, as I drew this as the 45-degree angle. So very incorrect on that part. But I don't know if I can make this up. Something like, yeah, I think I have to redraw. That's a shame. But what it should have been, let me just redraw this. That's my bad. So actually, I drew these points lying on the 45-degree 45-degree line, which wasn't wrong for most of them, but they should have stopped on the operating line as well. And what we wanted to do is that the first line initially, or I'm sorry, the first point, or I guess first pair, lies on the 45-degree line and the operating, something like that. And we said this was our xd, and that corresponded to a y1. Again, we had a corresponding, I don't know what color, corresponding x1 at our equilibrium curve, and that was x2, I believe. And now this is where the important part is. We stop at the operating line, because remember, the operating line is different from the 45-degree angle. Not all the points are equal to each other. I should say the composition that the pair of points receive or represent, the x and y's for the operating line, are not the same. That is strictly for the 45-degree angle line. And we started there because it was convenient. We knew our operating line had a point on the 45-degree angle line. That's why we started there. But as we come back down from our equilibrium, we hit a point where we have a corresponding, well, in this case, we had a corresponding vapor molar fraction, Y2 to our X2, and that was because they were passing streams on that equilibrium stage. So again, X1, Y2, we're looking at right there. Again, passing streams, mass balance, that's how we relate them all together. So that was my bad. I should have clarified that. Good thing I caught that there with the operating line. And really, there's no difference with the rectifying stage. We have our, I guess I'll just, a lot of drawing here. Our stripping operating line would be something like, so 45-degree curve. This is a Y1 and X1 binary diagram. And we'll start actually below here since we're stripping. It's our stripping operating line. So it will be something like, I don't know, that. And the whole point here is that we're going down stages. Well, you'll eventually see that the rectifying and operating line converge on an intersection, and you can actually go through a number of stages as you go down to this bottoms composition. And I should have related earlier that up here is our distillate composition. Assuming, of course, that our distillate mole fraction is equal to our vapor mole fraction, if they are in equilibrium. Is that what I said? Well, I don't know if it's necessarily equilibrium, but they are equal to each other. Yeah, so I guess I should copy down and kind of show why this point here exists. That's kind of me knowing that already, but I'll go ahead and write that out. So rectifying operating line. Did I say that was right here? I wonder if this will be hassle. Copy you down. Cool. So fine and dandy here. I think I said I was going to start at a point where we didn't need this, but I guess it's helpful. I mean, it's really easy. It's the very same thing as what I did before. We're assuming xn minus 1 is equal to xb. So our liquid mole flow rate coming down is equal to our bottoms, I'm sorry, liquid mole fraction coming down from the stage above is equal to our bottoms mole fraction coming out. And what that allows us to do is, well, I'll rewrite this in terms of the bottoms mole fraction. And eventually you'll see that they will, the vapor molar fraction will equal our bottoms fraction here. So as I factor this out, you'll have RB plus 1 minus 1. Well, what's the denominator? RB. Well, that cancels. That cancels. Yeah. Yn equals xb. So again, we have our bottoms composition. And that must be our yn. In this case, I'll call it, what did we call it? Y4? Is that our last stage? I should really just copy this down, honestly. So copy that here, paste it down here. So we said our bottommost stage was 4, so that is actually Y4. Did I make that all pink? Okay. That's funny. Okay. So yeah, we're looking at this down here. And remember, this is our Yn, so Y4, and our liquid coming down, so X3. And I think that in this case, n equals 4. And we're saying that if our liquid molar fraction from the third stage is equal to our bottoms mole fraction in stage 4, well, our Y4 must be equal to our bottoms fraction there. So that's just another visual. Yes, Y4. And you can probably already guess we're going to have a equilibrium. and that is corresponding to, or I'm sorry, did I say equilibrium? Let me think about this for a second. So y4 comes up, must be equilibrium with, did I draw this correctly? I think it should be wider. Oh, pause here. Let me gather my thoughts. Sorry about that. All right, sorry about that. I kind of got mixed up since we're going in opposite directions here, but we'll notice that we're coming from a y4 stage here. Well, this is an equilibrium stage, and what's going into that is our x, I guess x2. Is that what I want to say? Yes. So since we know our y4 from our boil up molar fraction was equal to our x3, since we know y4, now we know y2 or x2 because that they share an equilibrium in stage 3. So I believe I want to say something like x2, and once you know x2, you can actually get from your operating line, you have y3 now. Since again they're passing streams, so you use the operating line from our technically it's just a mass balance to relate those two passing streams. I think my drawing is correct. So let me pause again to kind of clarify that. That is the wrong thing. Let me here. Okay. Sorry about that. So I think I kind of understand now. So I was kind of confusing. So this XB, our Boyle molar fraction, is actually X3, and X3 is the one. Well, technically they're the same, but X3, if we look at our distillation column, X3 is in a equilibrium with Y3. Why we go up here, and now we have a Y3 on our equilibrium curve. So again, kind of guess very similar going up as we go through our different stages. So y3 corresponds to a passing stream of x2. So this is x2, and x2 has a equilibrium with, say y3 already. Or I'm sorry, x2 has equilibrium with y2. So we're getting near that feed stage. So I'll stop there. So again, very similar. We're going from one point to another is the general understanding of this thought process. So again, we said our xn minus 1. So in this case, I think our n, well, if x was 3, well, n had to be 2. So x3 was equal to our xb, our boil up molar fraction leaving the system. And if that was true, well, we found from our operating line that, well, n was 2, so y2, that's what I said. Well, yn was equal to xb, so it should be 4 here. So n is 4. I don't know what I'm doing. So n is 4, y is 3, because, geez, y is 4. Oh my goodness. Getting late. So y of 4 equals xb, so that was our first point. I'll call it x3, y4. And because we knew, going backwards this time, instead, remember in our rectifying stage, we use our y vapor for our corresponding operating line pair. Well, in this case, our liquid is what's going to be used in that case. X3 as a corresponding equilibrium pair, X3, Y3. Sure that's correct? Yes. So you're using whatever you have to find corresponding. So Y3 is in a passing stream here. 2. Why we have X2 as another point. That's the general gist of what we're going to be graphing. I think I want to also have the points as well ready to graph for the operating line. So how we're going to graph it is, again, points. I think we already discovered one of them. Yn is equal to xd, and xd is obviously xd, so that'll be 1 point, and then we need another point to graph it on. I don't know, maybe if x is 0, then we have just xd over r plus 1. So yeah, let's go with that. That's pretty easy. So just writing my points mainly for me. So rectifying operating line points. So the first point I'll be plotting is xd equals xd, y equals xd. Second point, well, I said x was 0. And well, you can kind of just look at it from the expression here. Well, if x minus 1 is 0, this whole term cancels. Oh, that's eraser. This whole term cancels out to, well, goes to 0. And then we're just simply left with this right-hand expression. So xd over y, xd over r plus 1. So those are the 2 points we'll be graphing. Circle that for itself. And then we have our rectifying. Did I write rectifying and stripping on the same one? That's really funny. Okay, anyways, I think this is supposed to be rectifying, yeah, or stripping. Oops. This is actually the stripping one. So one of our points, we said, go ahead, put stripping points. That recording. Okay. Stripping points. Yeah, operating line. And one of our points was already, like I said, x was equal to the boil up molar fraction, and y simply the same thing. Second point, I'd want to, again, this is arbitrary. I'll make y equal to 1, and then we'll have some point. Since if you remember, our binary xy diagram ends here at 1. It's actually 1. So if we plot y at 1, that's not. If we plot y at 1, it should reach somewhere here. Crossing, I believe, will stop around here. So maybe something like that. So at least we'll have a line crossing, or at least going through a good chunk of that binary xy diagram. So again, if I do something like copying down from this expression here, and now I'm substituting y for 1, and I'll solve for xn minus 1. Remember, I'll just write y and x's, but remember that the x molar fraction is coming from the stage above. So go ahead, write something like 1 equals, copy this down, rb plus 1, rb, xb, 1 over rb. And actually, this might be a little bit harder. So actually, you know what, going back to our first point, or my first point I made, remember that the boil up ratios are optional. This is just a kind of standard way of writing these, but we can actually go back to our original expression here for the stripping operating line. I'm going to go ahead and copy that. What happened? I'll go ahead and copy that and just substitute in 1 there. And this is just to show that both expressions are correct in when we're graphing the operating line. Oh, man. Some technical difficulties here. That. Calm down. Insert. Cool. I'll just leave it down there. So again, taking out the notation, y was equal to 1. Now we'll just solve for x. I just copied the same thing. I'm going a little, just a tad bit crazy here, but if I can remember it, let's not. What I want to do is relating the liquid and vapor molar flow rates instead of just the boil up ratio. So that is this one. Oh man, I'll use this. Yes, that is the one I want. It's getting late. Don't really want to think anymore, but oh well. Kind of chug along here. So again, 1, y equals 1, moving the notations. But yeah, we have, well, x2 for vapor bar plus v algebra at this point. Divide all of that by L bar. Checking. Yeah, should be good. So again, we said x is that in this expression here. Bother to write all that out, and y is equal to 1 right there. Okay. Before I go graph this, let's also derive the Q line. So again, Q line is line connecting the 45-degree line on the binary diagram, and hopefully my mic was picking that up. The binary XY diagram to the intersection of the rectifying shipping that intersection here. So to get that Q line, well, what do we want to do? This is me kind of just knowing, but the Q line is on the 45-degree angle. Way to derive that, but I think it's relating our intersections to Q. Let's just take a stab at this. Not really too sure where this will go. So we're gonna write our two mass balances for the rectification and our stripping stages. Actually, let me copy paste that so I'm not going crazy again. And this time we won't use the reflux ratios or the boil up ratios since it's not really what we want to do. This is rectifying. Hopefully there aren't too many mistakes so far. Still gotta code this, so gotta stay awake for that. So we'll have our stripping. That here, bars, copy paste that. Peace. That. And yeah, what we're gonna end up doing is to find this intersection. Well, we know x and y lie on the 45-degree line, and I guess I should stop and derive that after this. We'll go ahead and start with this since I know how to do it right now. This intersection is the derivation for that Q line, and what I'm going to do here is, I guess, just subtract across and find our x value. Actually, I think it makes more sense to start with y goes 45-degree line. I'll start there. Okay, so sorry about the pause there. So this is actually what we're going to use for getting our second point. So getting second points is I will get that intersection, aka intersection, but we should derive our Q line first. So again, using the same equations, our rectifying operation line and our stripping operation line. So using those two mass balances, we'll be able to get a the line for the Q line, and that's just by relating those in terms of Q. So what I'm going to do is, again, copy these down, but I'm going to keep the V's on both sides so you can see what this ends up becoming. See that? That's rectifying. This is our stripping. Kept the V bar. L bar minus XB B. So what I'm going to do here is subtract our two lines here. I believe it should be keep the vapor positive. We want the higher number first, so that will be V minus B bar. So doing some factoring here as I subtract these two mass balances, I guess. So V bar minus B. Subtracting across, we factor out xn minus 1. We have our... Did I do that right? No, it should be here on. So V is bigger than V bar. So that would be L minus L bar. And subtracting top from bottom. So plus XD B and minus some negative. So it's positive XB B. And what you notice here, we'll have some equations we can kind of substitute these terms for. Well, what is this? This is our basically what's going up from the top and what's coming out from the bottom. Well, that must be equal to what's coming in. And remember, this is for the more volatile component. So we have our feed, and it must be our component, more volatile component. So Z, and yeah, I think that's. I'm not missing anything here. Oh yeah, it's for our liquid mole fraction as well. So that is times Q as well. Since Q, remember Q is the liquid fraction of our feed, and these are our X's, so both liquids. Okay, what else we can do here? So again, I mentioned V minus V bar. I'm gonna keep that positive. Well, V minus V bar, let's draw this out here. There we go. So we had our feed, we had the liquid fraction of that, and we had our component, first component, more volatile component. And coming out, we had our V. Bottom below was V bar. Coming down was L bar. So liquid molar fractions coming down, or flow rates coming down, and vapor flow rates going up. Well, remember V minus V bar, it's these two relations. And what must that be related to? Well, it's our feed. So V bar, well, I should write feed of our, I guess, vapor molar fraction must be equal to the vapor going up minus the vapor going down, V bar, or I'm sorry, coming up from the bottom, because the vapor is the feed. That is vapor plus. So I just move that around. Let me make sure I'm not missing anything here. He added it to the other. Perfect. So what we have here is just another substitution. V minus V bar must be the feed. That is just the feed, that is the fraction vapor. And remember, Q is a fraction, so 1 minus a fraction, that's vapor. Must be the liquid. Did I say that backwards? Q is the vapor fraction, or I'm sorry, Q is the fraction that is liquid, so 1 minus the liquid molar fraction must be the vapor. Here we go. And then very similar thing here. And note that L minus L bar is negative because L bar is bigger. As you can see, L bar is bigger than L because we have a feed going down along with it. So very similar, it's just Q times F. And note that there's no Z term because you don't know whether or not these flow rates are what the composition of, if it's completely just more volatile component. So I'm just kind of writing everything here. Oh, this should be negative. And I guess we can get rid of these notations. Just remember what they're coming from. This helps visualize this a little better. I'm gonna move this down. There we go. There we go, and there we go. So, well, common factor here, get rid of it. F. They all have F, so we can simplify. We have Y times our composition that's just vapor, x times our composition that is a liquid, and added that to that is our component, our more volatile component fraction of our feed times its, well, it's the liquid fraction. I think I'm sorry. It shouldn't be all liquid, right? Yes, it should. Apologies. So that's actually not all the liquid from the feed because, again, that Q is not just our more volatile component. You can say our more volatile component is these two values because remember we wrote in our bottoms and our distillate in terms of our more volatile component, but Q specifically is just liquid fraction of the feed. It doesn't necessarily mean that the liquid fraction of the feed is all the more volatile component. So that's why we can't write a Q there. So now, just isolating y so we can graph this, we have negative xq over 1 minus q plus z q. So that is our q line. And I said we were plotting points. So to plot this point, we'll do something like if x equals z, we'll have negative zq q plus z q. And I'll just rewrite this so you can kind of see this better. Well, I'll combine the terms since same denominator. And now you can kind of see where I'm going with this. We're going to factor out the z so we can cancel out the denominator. That leaves us y equals z. So that is first point. That's why I mentioned earlier that y equals z, or I guess y our q line lies on that. I don't know how many times I've drawn this out, but our q line lies on this 45-degree angle where our x is at a z component, and I think in our, or I guess in my code I realize this is like 0.4 or something. But notice also that our denominator is 1 minus q, and if q equals 1, well, we'll have a divide by 0 error. So we can't just plug in a number and substitute to try and get a second point, which brings me to this next problem here. Just going back to this as an aside, if q equals 1, there's no way we can solve for corresponding x value if I just plug in 1, because, well, all of these will be 0. That's the whole point of trying to get our second point here. So, I wonder if I want to, yeah, I'll just write our points here. So, x equals z and y equals, that's number 1, our first point. Second point here, our intersection. So where our Q line is coming from our 45-degree angle line to the intersection of our two operating lines. And believe we're going to set these equal to each other. Let me check. What? I'll pause and try to make sure I don't get anything wrong here. Okay, so yeah, since we're setting them equal to each other, it's an intersection. So I'm just going to, I guess, factor out, well, this is 0, we're subtracting, so xn minus 1. Really don't need to call this xn, but kind of have it, I guess, xn minus 1, and we're subtracting. I want to keep this positive, so when I subtract, I'll have lv minus l bar over v bar. We'll have plus xd v over v. Subtract the negative, xb v over v. I mean, we're just solving for a point here, so it's isolating x minus 1. I'll have, well, these will move over to the other side. They'll be negative. I'll put a negative here, move it to the other side. Just some algebra at 10:30 p.m. So, and then we'll divide by our term here. And we could actually see, to get rid of this negative, I can kind of move it down here and apply it to get rid of that minus sign. So we'll have something like A plus L bar, B bar plus L over V. So that's just an expression we'll have for xn minus 1. And that's our first point. And to plug this in, again, just be coded as we graph our lines. So I guess I'll store that as like x intersection. And then when I plug this in, I can plug this into either of our equations up here. So I'll plug in that x intersection. So it'll be something like y equals x intersection. I'm close enough like here. X intersection times, I don't know, I'll pick rectifying. So L over V plus XD D over V. And yeah, I'll store that as y intersection. Now we have our second point, which will just be coded as x equals our x intersection, y as our y intersection. Cool. We have 2 points to graph all our operating lines. And that's after all this derivation. So I think we're actually done with the problem, but you know, we're visualizing. I'm a visual person, so go ahead and go to that lab. I want to do that. Let's lab this side. Can't. Well, hopefully you've written down those points as we'll be needing them as we graph them. So what I have pulled up here, trying not to write over our what we'll do calculations. I just remember we did a video on, or I did a video on the relative volatility. And again, this is just the import for our libraries, and we use CHE tools to define our bubble function. And with relative volatility, if you remember, we graphed our binary XY diagram just from some arbitrary two saturation vapor pressures we plugged in and related to as alpha. So that's what this is coming from. And then again, this graph is just, well, the binary XY diagram. It's our Y1 versus our X1, and we favor the vapor phase more. And yeah, we're going to be graphing right here. So I guess technically our initial variable should be right above. So again, these variables are something we'll need in the future as well. Well, I mean, right now, as we kind of code out our series of flow rates and what we need in our distillation column. So what I have here, just the feed is defined, and then the composition Z, as I've been writing in all my equations, that's the component of the more volatile component. I guess, yeah, composition, I should say. Q, remember liquid fraction. RD, here we go, is the, I guess, the kicker here. In terms of when we're defining our distillation column, we want to, what a common mistake is to define our both our purity and our flow rate at the top of the column. And what this could lead to is correct mass balance, something like if we say we want 0.4 moles per second coming out at the top for our more volatile component, well, can't do that if you accidentally said, well, if you know our initial flow rate going in is 0.3, that doesn't add up. You can't have 0.3 going in and 0.4 coming out of the top. That just, yeah, it just doesn't make sense. So that's why we have this new component here on the recovered fraction of the more volatile component up the top. And that way we'll be able to limit down all our expressions here. So you can kind of see, even just from this limited range of, I guess, defined variables, pretty much everything else in that distillation column is limited and can be written with our ratios here. So let's go ahead and kind of do our balance here. So remember our distillate, well, our distillate flow rate has a corresponding distillate composition as I initialized there, and that is our number of moles. So of our more volatile component, well, that must be equal to what's coming in. So what's coming in? Well, we have our feed times our more volatile component, and that is also times our, forgetting something here, distillate composition times our distillate flow rate must be equal to our feed flow rate of our more volatile component. And what I'm forgetting is the recovery. What I just mentioned is super important, so don't forget that like I did. So again, this is what we want to recover from our liquid, our component one of our feed coming in. So since that's what we want to recover, that's why we have it at the top relating to our distillate, moles coming out. So to get our distillate, we'll just divide by xd, and now we have an expression for our distillate, just like that. What else can we do? Distillate, I guess I should look up. Yeah, I wish I could show, maybe if I pull up OneNote here, I split my screen, and I do something like that. Yeah, there we go. So this actually is a lot better. Now we can look at what we need. Type. And I'm kind of in the way here, so I'll try to zoom in. Up. That should make myself smaller, but that's not the point right now. So, so we have our distillate as we related to a recovery now, and now what we can do is relate it to our bottoms. Well, remember that our feed is equal to our distillate and our bottoms. Well, if we want our bottoms, it's simply just b equal to, and I'll subtract over, so equals f minus. I guess I should also be labeling these. So this is the distillate flow rate, and this is the bottoms. Kind of see here is that writing expressions, so everything is limited just from these variables. So if we have bottoms, well, what do we want? We also want our molar fraction of the more volatile component coming out in relation to those bottoms. Well, that's similar to our balance up here. Remember that our bottoms coming out must be equal to 1 minus the recovery rate at the top. And again, this is for our more volatile component, our feed times our, well, volatile component, that fraction of our feed. What else can we do? So I think we can do, just jump into our reflux ratios. So remember reflux ratio, the optional way we kind of represented our operating line for both our rectifying and stripping regions. In this case, remember that the reflux ratio is L over our liquid coming down from the 0 stage right here over our distillate coming up top. Well, we have our R and we have our D, so that's just simply R times D equal to RL. That our liquid, well, now we have, can we do L bar? Yeah, we can do L bar. So L bar, so remember L bar is the liquid molar flow rates coming down, and since these are our constant molar flow rates, as I mentioned at the very beginning, with the heat of vaporization not changing with composition, well, these are all constant, so all of these L2 and L3 bar are both L bar. And remember that L bar is different from the L up top in the rectifying stage because we have this feed coming in. So L bar must be equal to, well, our liquid coming down from the rectifying stage, plus, and that should be our liquid fraction of our feed. That, and then we should be able to do our vapors here. So vapor at the top, well, vapor going up top must be equal to liquid coming down and distillate out. I think I can just, that just is vapor equals liquid plus distillate, and V bar must be equal to, well, V bar is going in, so it must be equal to, or I'm sorry, V at the top, our vapor molar flow rate coming up top must be equal to the vapor flow rate from the bottom, V bar going in, plus our vapor fraction of the feed. So V plus our vapor fraction of the feed, 1 minus Q. Remember, Q is a liquid, so 1 minus that is our vapor times our feed. Hopefully we have everything we need to graph every point we have written. So yeah, I think that's all we need. So I'm gonna go ahead and shift enter. Doesn't yell at me, hopefully. Did I do? Oh, I didn't set it equal. So this was actually XB, and the mass balance for the bottoms, I just want to divide by B. Oh, there's more. F not defined. Funny. Guess I need to rerun everything. It's probably worth it, in case, you know. Yeah, so we can actually go straight to graphing. Let's make it under our, so remember this is from our relative volatility binary XY diagram. And if we want to graph our points, well, I think I'll use this since this is graphing a point. Maybe you don't have to go too overboard here, but this will be our, let's start with our rectifying operating line. And I don't know, make it a different color. 0. What else? So these will not be the same points. Let's see if we can find our points here. Here we go. So for rectifying, we had points. That's what we derive from our expressions here. X was equal to xd, and other x was 0. I think zeros should actually go first. Lower range, xd. So since 0 is first, have our expression first, xd divided by r plus 1, and xd is d. Actually, think it matters, the order. I guess we'll find out. Go ahead and copy paste the next one. So now we're going to be graphing our stripping operating line. Go ahead and make that the same color. Why not? I should memorize some RGB colors just for fun. So have our stripping derived. One of them was DXB. We discovered that they were equal to each other at that bottom stage. And the other one was this expression. We have parentheses, the bar. Okay. Okay. Plus xp times v over our liquid flow rate, L bar. That corresponded to y equals 1. Did I do that right? xb, and b bar, xb over L bar, and y was equal to that. Let's go! First try. So we got our 2 points here, graphed in red since RGB, so 100 on the first parameter there. And now we want to graph our Q line. So too bad. Well, we already did it. All the work's there. We're just copying it down. Need to find it. So let's start. Where are we? We have our expression for our operating line, but all we need is actually the 2 points. So we actually have our z's already defined here. This will be set on go Q line. So I might want to leave some space here for when I define our intersections. So 1 point is just at z, above z, bad period here. And then our second point are these two expressions here. So what do we have? Our x intersection. Sure if the dash is okay. Let's use underscore. So our x intersection. We're storing that variable as our expression here. So bit of an expression there, kind of long. xd, our distillate molar fraction, times over v. And remember, this was just the intersection. We took our two operating lines and simply subtracted across. So xd times d over v plus xb, our bottoms molar fraction of our more volatile component, times v over v, our bottoms over our vapor. Be surprised there's no bar there. Okay. I think we should be missing a bar. So v bar here, yeah. I missed something. So b over v bar. What else? xd b plus xb times b over v. Yes. Okay. All that divided by our L bars. So liquid flow rate from the bottom divided by vapor flow rate in the bottom plus our liquid flow rate at the top divided by our vapor flow rate up. It doesn't yell at me. Nothing happened yet. Z is not defined. Oh, I guess we called it Z, right? Oh, that should be. Where did I put it? Technically, that's C. Okay. Now we want to define our Y intersection. And remember that this was just plugging in our X intersection at any of our operating lines. And I think I chose rectifying. So I just plugged X intersection into here, our rectifying operating line. So that's just L over V plus our split molar fraction times P over V. Yell at me. Okay, and now we want to graph that. So that would just be intersection and Y enter. See that? This not quite what I want to, but oh well, this works. So I don't think we need to go back anymore. Okay, so that is wrong. So our Q line is not going at our intersection, meaning our expression is wrong here. So let me go double check what the correct expression is. Okay, so I think I found error here, just simple algebra mistake. Right here, when we divided by our liquid and vapor flow rates, this expression here divided to the other side, I changed it to a negative, which is correct, but I didn't do it in the correct order. So if we rewrite this as it is, divide like normal. So we had our L bar, or I'm sorry, our L over V minus L bar over V bar. And if you apply the negative to that, well, that becomes negative LV plus L bar over bar. So that's actually what we wanted to do. So let's put that right in. Oh, you couldn't see that right. So right here is what I'm talking about. Let's go to collab. So again, L bar over V bar minus L over that. Awesome. Got our straight line. And remember, this is a straight line because our Q is 1. And if you remember from our expression, it was 1 minus Q in the denominator. So all that work for vertical line. So what? Well, the importance is that now we have all these equations defined. If we change our Q, we'll actually have varying, our lines will change with them. So we don't have to recount for that again. They should change with them, maybe. I did something wrong again. Did I run everything? Oh, here we go. Divide by 0. What is a 0? dB is somehow 0. Interesting. I was hoping to be done, but I guess we'll have final error to troubleshoot. Okay, so from what I can surmise, it's basically that our liquid fraction was too low, that we were getting a divide by zero error in the rest of our expressions here. And yeah, once I changed it to an actual liquid fraction that works, I can see the line is changing. So our Q here is trying to match that point of intersection of our rectifying and our, so rectifying is coming down like this. Our stripping is coming. I don't know, the mirror image of the camera is kind of hurting my brain, but there we go. We have our Q line, and hopefully that is the end of this over that. So hopefully we managed to do everything. Homework. Now it's only part A, so look forward to the next parts and how difficult it will be for me. So yeah, just kind of a summary. We did our constant molar overflows using that assumption that the heat of vaporization does not change with composition. We found our vapor and liquid rectifying and stripping operating lines. I'm sorry, rectifying and stripping operating lines. After deriving those, finding 2 points, graphing them, and we also did the same thing for the Q line where we used those 2 operating lines, found an intersection, and found another point where we assumed, I believe, Z was equal to X, and that meant that the Q line rested on the 45-degree line as we derived. So yeah, that's that. Hopefully you kind of understand how, well, I mean, now I understand how the operating lines are super helpful in getting all those polar compositions, the vapor and liquid compositions in each stage. So yeah, this homework. See you in the next part.